Hello, welcome to the Palaeontological Association Conference 2020. I'm Victoria Edgerton, and I will be chairing the Comparative Morphology and Feeding B session. And so this is session number 8, So with the session, as always, if you have any questions, please put them in the Slack channel for session 8. And we're going to start with the first talk of the late morning, on cranial muscle reconstructions, quantify adaptation for high bite forces in Oviraptorsauria by Luke Mead.
Hello everyone, my name is Luke Mead and I'm currently finishing up my PhD at the University of Birmingham working with Dr. Stefan Lautenschlager. My research focuses on the functional morphology of the cranium of Oviraptorosaurian dinosaurs. And in this talk I'm going to take you through work I've done with my fellow PhD student Fionn Ma on reconstructing the jaw musculature of these dinosaurs, assessing their bite force and constraints on their jaw gape in order to better understand how they may have been feeding. Oviraptorosaurians are a group of theropod dinosaurs from the Cretaceous of North America and Asia, and the group evolved distinctive and highly modified skulls that are lightweight but have expanded space for musculature and robust toothless beaks that suggest they may have had powerful jaws. They're of interest as one of the few theropod groups thought to have evolved to be herbivorous, though specialised feeding habits have been suggested for them, such as durophagy, so specialising in hard foods, perhaps shelled mollusks or tough plant material. But in this study, we use digital techniques to reconstruct their jaw musculature to assess what their peculiar jaws were capable of. We estimate whether they could actually bite hard and how their jaw muscles might have restricted the angle they could open their mouths. This work was based on CT scanned datasets of the crania of 4 species from the Cretaceous of Mongolia and China. We looked at Incisivosaurus, the earliest diverging Oviraptorosaurian from the early Cretaceous of China. This species is notable for being one of the only members of Oviraptorosauria to have teeth, in this case weird, elongate, incisor-like front teeth, hence its name. The other 3 species studied are later diverging Oviraptorosaurians. The Oviraptorids being one of 2 main groups within Oviraptorosauria, the other being the Caenignathids, but they unfortunately have poorly preserved skulls. Citipati, Cairn and Conchoraptor are from the late Cretaceous of Mongolia, from 2 formations in the Gobi Desert, and have pneumatic, superficially bird-like skulls typical of these late Cretaceous Oviraptorids. The 4 species that we looked at give us a variety of skulls to assess if musculature changed from early diverging members of the group to later Oviraptorids, and how much variance there was in cranial function within the Oviraptoridae themselves. The CT datasets were segmented in the software of Viso, but after this they needed to be restored from the state you see here to an in-life condition, and this was done in Blender. In the case of Incisivosaurus, this involved mirroring a large number of cranial elements over from the more complete right side to the left, correcting a significant shear deformation and mediolateral flattening. The mandible was constructed using photogrammetry on available fragments, with some interpolation over missing regions. Citipati required very little restoration from its CT scan state, essentially just correction of some slight shear asymmetry between its left and right sides. Again, the mandible was created using photogrammetry. The Cairn specimen required a more significant amount of work, repositioning fragmented bones and reversing compression, especially in thinner areas and pneumatic spaces of the cranium. The mandible was included in this CT dataset, so restoration was similar. The final specimen, Conchoraptor, was very incomplete, so the CT scanned elements were combined with a photogrammetric model of another incomplete Conchoraptor cranium to make a more complete composite. Finally, we again used photogrammetry to construct a mandible model for Conchoraptor, and this completed our dataset of 4 skulls. The models then formed the base for a digital volumetric reconstruction of the cranial musculature in each species. The origin and insertion sites of 8 cranial muscles were identified based on the skull morphologies, studies of related theropod groups and extant analogues, our interpretation of which you can see here. This work is currently in peer review, so from this point onwards, please don't tweet any of our results. To reconstruct the extent of the muscle volumes, bundles of 8 Bezier curves were created in Blender as a simple path between the identified origin and insertion sites of each muscle, following their likely path and avoiding intersections between bone and other muscles. We then shrink wrapped a simple shape, a subdivided sphere mesh, around these bundles of curves to form a convex hull, and these simple volumes were then expanded equally in the software Viso until they touched and reached their limits, filling out the skull's available space for adductor musculature. These muscle volumes were then smoothed to form the final reconstructions, and we calculated bite force estimates based on the reconstructed muscle's cross-sectional area, their angle, and in-lever and out-lever measurements of different bite positions. The resulting muscle volumes are shown here, successively stripped away to show them all. We found the condition in the oviraptorosaurian skull is characterized by an increased volume for adductor musculature and increased mechanical advantage resulting from the anteroposteriorly shortened skull, compared with the more conventional skull geometry of the earlier diverging Incisorosaurus. Estimated bite forces conserve a greater proportion of the resultant force applied to the mandible in the oviraptorids compared with Incisorosaurus, and that's from a greater mechanical advantage in the oviraptorid's jaw for all bite positions that we measured, though the difference relative to Incisorosaurus is greatest anteriorly. In all species, the musculature was also required to curve around the presumed space for a large eyeball. They've all got large orbits, and that was actually superficially similar to modern parrots. Looking at the actual estimated values, we see an increased relative bite force in the oviraptorids of 17 to 84% greater, depending on species and bite position, than we would predict by scaling up the bite force from Incisorosaurus based on cranial surface area. This increased relative bite force in the oviraptorids is not a result of more beneficial muscle insertion angles. There's no clear difference in the ratio of resultant muscle force acting on the mandible to the total muscle force produced between Incisorosaurus and the 3 oviraptorid taxa. The greater bite force is the result of increased musculature and greater mechanical advantage from the short oviraptorid skull. To give some context for the values, the bite force of Incisorosaurus is about that of a large rabbit, and Citipati is about that of a human or medium-large dog. The relative contribution of the different cranial muscles to bite force is broadly similar in each species. The PTV, the ventral palatal muscle, is typically the largest component, but Citipati is actually the most different from the others, with its wide sloping posterior of the skull that allows the muscles of the external adductor group to be larger and better positioned, while the palatal muscles are less vertically orientated and relatively weaker. And this is potentially indicative of Citipati having a stronger vertical crushing bite with less emphasis on anteroposterior grinding jaw movement. And in addition to body size, that could hint at an element of niche partitioning between Citipati and co-occurring oviraptorids like Khan. No clear difference emerges between Incisorosaurus and the later diverging oviraptorids in the relative contributions of cranial muscles to bite, apart from a slightly weaker pseudotemporalis group. Reconstructed muscles are proportionally similar but relatively larger in the oviraptorids. Force estimates of the 4 oviraptorosaurians, including Incisorosaurus, are significantly stronger than estimates using similar digital methods made for other herbivorous theropods of much larger body mass, both relatively and absolutely. These results suggest that oviraptorid oviraptorosaurians, and to a lesser extent earlier diverging oviraptorosaurians such as Incisorosaurus, significantly differed in cranial function compared to other herbivorous theropod groups, both of similar size and of much larger size, so they were potentially feeding on very different foodstuffs. Oviraptorids shared an environment with both ornithomimosaurs and therizinosaurs, and other additional herbivorous dinosaurs such as ankylosaurs, hadrosaurs, and sauropods. Strong bite forces may have allowed oviraptorids to acquire and process tougher plant material than these other groups, or to specialize in hard nuts and seeds. High bite forces, though, do not necessitate dietary specialism to the specificity of molluscivory, for example, and instead they may have widened the range of possible food sources, with oviraptorosaurians potentially being effective generalists or specialists depending on the environment. Next, we wanted to assess if our muscle reconstructions could be used to constrain how wide these dinosaurs could open their jaws. We used Blender to animate a jaw opening cycle in which the muscles were modelled as two simple cylinders connecting the rostralmost and caudamost extent of the muscle's origin and insertion sites. A Python script was used to measure the length change in the muscle cylinders throughout the jaw opening cycle, and constraints on how the muscles could stretch were based on values reported for muscles' inherent strain range over which maximal tetanic contraction can be achieved. Using these constraints, we estimated the gape angle, which was the limit of optimal tension in muscles when that was reached, and the maximal gape limit that might occur for muscle tension to still be possible. The early diverging Oviraptorosaurian Incisivsaurus showed the highest estimates of optimal and maximal gape limit. The Oviraptor showed lower values, and estimates for Kahn were the lowest. The rostralmost cylinder, representing the ventral palatal musculature, constrains optimal and maximal gape in all species apart from Citipati, which is constrained by the rostralmost regions of the superficial external adductor. And this reinforces the finding that relative muscle strength and arrangement in Citipati actually has more differences compared with its fellow Oviraptorids than the Oviraptorids do generally compared to the early diverging Incisivsaurus. The Oviraptorosaurians show estimated gape limits similar to herbivorous dinosaurs like Erlikosaurus, with the Oviraptorids being even more restricted. It is noted that herbivorous species tend to exhibit lower gape angles than carnivorous species, and thus our estimates of small gape angles may be further support for herbivorous diets amongst Oviraptorosaurians. The maximal gape angles estimated for these Oviraptorosaurians are similar to experimental results on the gape angle in birds, which can reach around 40 degrees, and this is a functional similarity between the crania of birds and Oviraptorids, which beyond superficial beaked appearance are quite dissimilar. To conclude, muscle reconstructions show Oviraptorosaurian dinosaurs were capable of producing strong bite forces, especially relative to other herbivorous theropods. Oviraptorids themselves were probably predominantly herbivorous, generalists or specialists depending on the environment, and their jaws were constrained to relatively small gape angles. Bite forces vary greatly between Oviraptorids and herbivorous theropods such as therizinosaurs, and that's more so than estimated gape limits. So bite force was probably the more important niche partitioning component of cranial function. Cranial shortening and expansion of muscle space was the driver of the increased bite force from early diverging Oviraptorosaurians in the evolution of Oviraptorid Oviraptorosaurians, but muscle arrangement remained fairly conservative. We would like to thank the following people for data access to specimens and for supervision, and I hope you have enjoyed our talk and have a great conference.
Great, thank you. Again, welcome everyone to the Comparative Morphology and Feeding Session B. Our next talk will be from Antonio Bellel, the dental form and function in feeding diversity during the early evolution of Dinosauria.
Hi, thanks for attending my talk. I'm Antonio, and I'm going to present part of my PhD on the dental form and function in early dinosaurs. Dinosauria originated in the mid to late Triassic, and early in their evolution, they achieved a remarkable diversity of craniodental morphologies, including forms with robust jaws and hypertrophied teeth, others with gracile skulls and numerous tiny teeth, and others with heterodont dentitions. But despite this diversity of dentitions, three main tooth types are usually identified and can be related to the main dinosaurian clades. First, sharp, curved, and serrated teeth, which are typically seen in theropods and herosaurids. Spear-shaped teeth with coarse denticles, present in later diverging sauropodomorphs, and triangular cusped and cingulated teeth, which are common among early ornithischians. So the ecology, and in particular the feeding and the diet of the earliest dinosaurs, is key to understanding the evolutionary success of this clade. Tooth morphology, in comparison with extant taxa, has formed the basis for most of these inferences. And in this context, the diets of early dinosaurs seem to be quite varied because they share dental configurations that resemble those of different extant taxa with a range of feeding habits. Of course, this approach is qualitative and has its limitations, but new computational and statistical methods offer the possibility to quantify shape, simulate function, and perform ecological classifications based on them. So we thought that these approaches could resolve the feeding diversity of early dinosaurs and the diet of the last dinosaurian common ancestor, which is contingent on different phylogenetic hypotheses and new fossil findings. So the main aim of our study is to quantitatively characterize the diversity of dental form and function in early dinosaurs to support ecological inferences of diet, and by investigating questions like how good tooth morphology and function can be at predicting diet in fossil taxa, what are the most important aspects of tooth morphology in early dinosaurs, and how different tooth types would have resisted feeding relating forces, what is the relationship between tooth form and function, and at the end, were early dinosaurs as diverse in dietary preferences as we think. So to test this, we compiled CT data and 3D model data sets of extant sauropsids, dentitions, including species of crocodilians and squamates. The data sets were downloaded from Morphosource, and so we are grateful to the scientists that made them available. And the species show a wide spectrum of feeding preferences, and were classified in three groups: carnivores, omnivores, herbivores, insectivores, and europhages. And we were able to get CT scans of 11 early dinosaur taxa from researchers around the world. Many thanks to them. These dinosaurs include two ornithischians, the Herasaurid Herasaurus, the early divergent theropod Eotromius, and 7 non-sauropodiform sauropodomorphs. First, we created 3D models of tooth crowns by segmenting CT data and cleaning surface models. And to study function, we created finite element models of teeth. The models were constrained at the base and loaded at the tip, simulating a bite force. Von Mises stress and element volume were used to calculate mesh-weighted arithmetic mean, which is the mean stress of the model corrected for mesh heterogeneity. And the intervals methods was also applied to the FEA outputs, dividing the elements of the mesh into intervals of stress that are then submitted to a PCA to visualize variation in stress distribution. And both of these statistical methods were developed by Marcel Huguet and colleagues. Then we looked at tooth morphology by quantifying it using 3D geometric morphometrics, a combination of anatomical landmarks, curve and surface semi-landmarks were used to capture shape of the tooth crowns. Surface semi-landmarks were transferred from this template to the models using a semi-automated function in R. And after sliding, landmark coordinates were aligned using a procrustes analysis and later submitted to a PCA. And these are the results of the FEA. The 5 dietary groups have different patterns of stress distribution. Carnivores show generally higher stress with similar distributions to cantilever bending. The other dietary categories, especially gyrophages, show generalized low stress, but herbivores show more varied patterns of stress distribution. And among dinosaurs, those with curved teeth like Eudromius, Herosaurus, and the earliest sauropodomorphs show large areas of high stress like extant carnivores, differing from the low stress patterns of Lesothosaurus and later diverging sauropodomorphs. These patterns are also evident when we look at the mean stress values. The dinosaurs with with the highest stress are Eudromius, Herosaurus, Bureolestis, and Eoraptor. Lesothosaurus has the lowest mean stress values, while Saturnalia and post-Carnian sauropodomorphs sit between with low to moderate stress. And when we visualize the stress intervals in a PC1, PC2 morphospace, we see that carnivores occupy the largest area of morphospace, corresponding to the intervals with the highest stress. The space of omnivores and insectivores largely overlap in areas of low stress intervals, and herbivores occupy a larger area corresponding to intervals of low to high stress. So along positive values of PC1, which are indicative of higher stress, we find Herosaurus, Eudromius, Bureolestis, and Eoraptor, and also Manidens. And towards negative PC1 and on the herbivorous region, we find Saturnalia and the postcarnian sauropodomorphs, except for Ticodontosaurus, which has an intermediate position, and Lesothosaurus plots on the area of low stress intervals. Moving on to shape data, here's a morphospace of the first 2 PC axes. PC1 shows transformation of the apicobasal height of the crown from the dome-shaped teeth of gyrophages and some herbivores to the left to the piercing teeth of carnivores to the right. And PC2 is separating blade-like teeth from spear-shaped teeth. So basically explaining tooth crown curvature. And PC3 explains variation in tooth complexity from multi-cusp teeth, like those of ornithischians and postcarnian sauropodomorphs at the bottom, and towards negative values to simple conical teeth. And finally, when we visualize all 3 PC axes together, we can see that Eudromius, Herosaurus, Bureolestis, Eoraptor, and Saturnalia occupy areas around the carnivorous region with simple, curved, blade-like teeth. Postcarnian sauropodomorphs with straight lanceolate and cusp teeth occupy an intermediate position between carnivores and herbivores, and Lesothosaurus plots in the herbivorous area with low cusped crowns. And then Manidens occupies a unique area with tall multi-cusped teeth, which indicates its highly specialized dentition. So to wrap up, the main conclusions of this morphofunctional analysis are that tooth shape and stress patterns discriminate well between carnivory and outdoor diets, while herbivores, omnivores, and insectivores mostly share similar morphofunctional traits. The main aspects of dental variation in early dinosaurs are crown height, curvature, and tooth complexity. The teeth of carnivorous taxa experience higher stress than the rest, and durophages show the lowest stress. And some similarities in the patterns of morphospace occupation from morphometric and stress data are appreciated. So Herrerasaurus, Eudromius, and Carnian sauropodomorphs appear to be carnivores. The Sothosaurus was probably a herbivore, and postcarnian sauropodomorphs occupy intermediate positions. So this is reflecting these quantitative analyses are reflecting that form and function and an early diversification of diets in dinosaurs. And so for future works, I would like to apply machine learning algorithms to perform ecological classifications and do mechanical testing to investigate tooth efficiency of different tooth types. So yeah, I wanted to thank these people, my supervisors, people that provided data of dinosaur and extant taxa, and
thank you, Antonio. I'm sorry we were starting to run, but thank you so much for such a great talk and looking at the diet of early dinosaurs. Excited to see more work on that. So our next talk will be diet of the toothed and long-snouted longipterids, birds determined with reference to quantitative analysis of extant bird dietary proxies. And again, remember everyone, you can put your questions into the Talks 08 Comparative Morphology section in Slack. Take it away.
All right, thank you, Victoria. So my name is Case Miller. I am a PhD student at the University of Hong Kong, and we're here to talk about some weird birds, specifically figuring out what their diet was based on actual numerical comparisons. And I will point out really quick, all of this data is still preliminary, so please do not share any of this on social media. So what are longipterids? They are the long-snouted enantiornithines. Enantiornithines were the dominant birds of the Cretaceous period, and Longipterigidae are this weird group that all have very elongate rostra with all the teeth clustered at the front. Because they have such weird rostra, then there's been a lot of dietary hypotheses. So earliest ones proposed that Longirostravis was a mud prober, Longipteryx was specialized for catching fish. Not really a lot of information given why, just they have long rostra and it makes sense to that particular writer. As it kept going on, more things were being put into that probing category, modifying from mud probing, bark probing, etc. But ultimately, not really anything backing up any of these claims. So some of you might remember that at last year's PalAS, myself and my supervisor presented this framework that we've gotten from the literature in order to figure out what the diet of fossil birds is, looking at what works in living birds and fossil theropods to figure out what could actually make it work. Unfortunately, some of these require in-person data, which is not super easy to get when your train has to go through Wuhan to get to the museums. So unfortunately, we have had to set 3 of these aside for now, but there are still 4 that we've been able to get information on, working with museums, getting pictures, things like that, as well as then making it, so we've been able to apply it to 4 of the 5 longipterygid species, as well as 173 extant bird species. So what did we see? Well, body mass is not super diagnostic overall. There is a pretty big range of body mass that can be for any given diet. However, among carnivores and herbivores, you can see there seems to be some bimodality there. And just for reference, all longipterigids, the largest are around 200 grams, smallest around 30 or 40. These are relatively small animals. And so when we actually then took the carnivore and herbivore data and tried different combinations to see how they split, We found invertivores and vertivores split pretty well in carnivores, folivores, frugivores, and granivores, nectarivores as each individual groups within herbivores. And then we use what's called the Uden index, often used for determining serum values for diagnosing diseases to get mass cutoffs. Big takeaway, all longipterigids are well below these cutoffs. And so they're most likely invertivores, granivores, or nectarivores. So then traditional morphometrics. So traditional morphometrics of bird claws specifically have not seen a whole lot of diet specifically, but of raptorial style. So obviously if it's a raptorial bird, likely has some element of carnivory in there. And so from our PCA, pretty much everything is plotting far even less recurved than ground birds, pretty solidly in ground bird territory. Our LDA predictions actually did find a little bit of proclivity for suffocating raptorial style, so owl-like, in specifically Longipteryx. It's mainly driven by it having a relatively large digit 4, which is also true in extant owls. All right, mechanical advantage. I'm sure when all of you saw the PCA, you cringed like I did the first time I crunched these numbers. That is not a clean plot. Unfortunately, mechanical advantage has not been super diagnostic among birds. Already some of the literature has shown that, but we still want to try because it works in a lot of fossil theropods. There are a couple groups that are distinct here, husking granivores, as well as folivores and tetrapod hunters separate somewhat, and so we can at least rule them out for longipterigids. But even with LDA, the best predictions in vertivores and generalists are also the ones that span most of the morphospace, so it's probably just a default prediction. All right, finite element analysis then. As Antonio just explained, mesh-weighted arithmetic mean strain, good summary statistic for FEA models. And so again, broad overlap across diets, but this high strain region, so relatively weak jaws, is only inhabited by carnivores. And all of our longipterigids except Shanwayano are in a space that is only carnivore as far as how high their strain goes. And then when we expand that to the intervals method, where we can get not only a measure of what the relative strain value is, but also the strain homogeneity. So over here, these are taxa that have relatively inhomogeneous strain. They have big peaks and large areas of low strain. These guys tend to be intermediate throughout. And so we can sit, and so we'll get some separation along there as well. And again, our longipterigids solidly within carnivore only space. Herbivores start about here. They are pretty solidly carnivores. And so what's interesting is we do get a couple herbivorous predictions from LDA. Those seem to be somewhat of quirks. Nothing else really points to them. So again, looking mostly here, invertivores, piscivores, and generalists seem to be the most likely predictions based on our FEA results. So let's put it all together. So the ones that are telling us the most here, finite element analysis was able to actually narrow these down pretty well. So invertivores and piscivores are the most likely there, but then we also know that they're not likely to be a piscivore based on body mass. They're much lighter than any extant specialist piscivore. So that narrows it down to invertivory, which does agree with the mechanical advantage results as well. And then Longipteryx in particular has some raptorial characteristics, so might be grasping those inverts, similar to modern small owls and falconets, whereas most other longipterigids do not have that. And so more likely, at least from this data set, are more likely going to be ground foraging. I will note, again, this data is preliminary. We've actually had a bit of a mix. We've had a bit of a shakeup with the traditional morphometric, so expect different in the final paper. Then there's Shenjing-Ornis. I haven't talked much about Shenjing-Ornis because I don't know what it does. The body mass falls within the error bars of our predictions, inconclusive. The skull is just too fragmentary to reconstruct, so can't do anything with MA or FEA. So all we know from the traditional morphometrics is it probably wasn't a raptor. So other than that, I could not tell you what it's doing. Big picture then. Other than Shenjing-Ornis, diet seems pretty conservative. Invertivore is still a broad category. These things could be doing different things within the invertivore space. But there is a question of if this rostral specialization is actually a dietary specialization. There's been a lot of recent papers proposing that invertivory is the ancestral enantiornithine diet. So if these things are having such a divergence from other enantiornithines, but aren't having a dietary divergence, then maybe this is not actually a specialization for that. There's lots of other possibilities. ectoparasite loads are recorded from several areas in Myanmar. Could be something with temperature regulation like extant toucans. And some of these have been proposed in passing. I think they should be explored a little bit more thoroughly with this result. We also failed to reject hypotheses that Cretaceous avialans were low mid-order consumers. So usually when we're reconstructing J-hole food webs, birds are just kind of stuck in the, oh, they probably ate bugs. And there's not been a lot of proof backing that up, but we do fail to reject that hypothesis. It seems like that is the most likely thing that they are doing. And then we have a big increase in quantitatively supported non-avian avialan diets. So I'm really interested to see what is the ancestral non-avian avialan diet. We know that it looks like there's a big dietary radiation as we hit 80s. I want to know how deep in time that goes. So what comes next? More birds. There's so many different avialans that are essentially the same as this. We're just a spitball for what their diet could be. And so I want to get out and test more of those. You also might have noticed several of those diet categories were definitely undersampled, having as few as like 3 representatives. And so trying to get more extant groups to try to get those results more robust. We definitely need to refine mechanical advantage. Already we've done a little bit of that. With some of the reviews we've gotten back, we've got a bit more separation. So that's looking good so far. And then of course, those in-person lines of evidence, working on it, already getting some wheels turning with getting measurements taken by people that are already in the museums. But that is for now going to have to be a separate paper. And with that, just wanted to give a big thanks to all the people on screen. No way I could have collected all this data just by myself, hoofing it. So huge thanks to all of them, as well as Research Council of Hong Kong and University of Hong Kong for keeping the lights on. All right, thanks everyone, and enjoy the conference.
Thank you so much, Case. What a great talk, really interesting. I'm sure you'll have lots of questions in the Slack channel. And if I can remind everyone that our presenters will be on the Slack channel answering questions as they go. So also if speakers could also please keep in mind that the Slack channel is open and take a peek to see what great questions are going on there. So our next speaker is Richard Jordan, and it's the Carboniferous Chimera suck. Evidence for high-performance suction feeding in the Pennsylvania stem group Holocephalin Enopera.
Is that working?
Yep, can see it just fine.
Awesome. So hello, I'm Richard. I'm at the University of Birmingham, but when I did this, I was at the MNHN in Paris with Alain Pedel and Anthony Harel. And in this talk, I'm going to try and persuade you that this little fish, which was a relative of ghost sharks, was a high-performance suction feeder in the Carboniferous. So suction feeding is where you feed by creating a pressure gradient down which food moves into your mouth. And this isn't a very effective feeding strategy in air unless you're Henry the Hoover, but underwater, it's an extremely effective way of getting prey into your mouth. And you basically need 2 things to be able to suction feed. You need to be able to create this anterior mouth aperture that you can point at whatever you're going to eat, and you need to be able to expand the space behind it to create this pressure gradient. And jawed vertebrates, or gnathostomes, are really, really good at suction feeding, and they've evolved various ingenious ways convergently of becoming efficient, high-performance suction feeders. And the kind of supremos of suction feeders among living gnathostomes are actinopterygians, particularly neopterygian fishes. And they have this very complicated network of dermal skull bones that they use to create the conditions for suction feeding. And the evidence for this appears in a fossil record in kind of the late period, and it's supposed to be one of these things that's let them dominate aquatic faunas ever since. But you also get other bony fishes that suction feed. This is a sarcopterygian, or a tetrapod, which is a mata turtle. And this obviously doesn't have all these dermal bones, so it's suction feeding with a very kind of big hyoid skeleton and big pectoral girdle. And you kind of see similar morphologies in other tetrapods, like some kind of salamanders and some frogs. And rather alarmingly, I read that a walrus can suck the skin off a dead seal, which is something to think about while you eat your lunch. It's not limited to bony fishes. You also get cartilaginous fishes that suction feed. So again, several times convergently, it's evolved in sharks. This is a bamboo shark, and it kind of creates this anterior mouth aperture with these labial cartilages and expands its pharynx with a big hyoid skeleton, and then uses its pectoral girdle to kind of pull prey down its long, sharky pharynx. But there is one exception to this gnathostome suction feeding bonanza, and that is holocephalans, the 4th major group of jawed vertebrate. And instead of being high-performance suction feeders, all living holocephalans are durophages. They kind of live demersally, and they crush hard-shelled prey on or near the sea floor, like these hydrolaguses you can see feeding on oysters. And they're highly specialized to do this. They've got this upper jaw that's fused to the brain case in what's called holostyle. There's a very short lower jaw with a high mechanical advantage. They've got these hypermineralized tooth plates for actually crushing stuff. And they've got these enormous mandibular adductor muscles that attach kind of preorbitally onto the skull. And they loop around the lower jaw in this submandibular sling that's supposed to help mitigate the high forces they generate. And all living holocephalans or chimeras or ghost sharks, whatever you want to call them, are adapted to do this. I use the word all kind of loosely because there's only like 50 to 60 species of living holocephalan compared to like 50,000 species of jawed vertebrate as a whole. So they're a tiny slice of jawed vertebrate diversity. Most of them live in the deep sea. They're all very morphologically conservative. They're very strange animals, but kind of in the same way. And they all feed doing durophagi. But in this talk, we're going to visit holocephalans in the Carboniferous. And a living holocephalan that could read the scientific literature would be astounded at the range of Carboniferous holocephalan body shapes and feeding morphologies. There are holocephalans that kind of look like sharks, ones that look like eels, ones that look kind of like living holocephalans, and ones that look ostensibly kind of like neopterygians that you get today. And these things are feeding in loads of different ways. Some of them have generative tooth sets like sharks. Some of them have like big durophagous crushing tooth plates, and others we don't really know what they were doing. They just kind of look weird. And this is important because the Carboniferous is a kind of a formative period in the evolution of jawed vertebrate ecosystems. All of these taxa that used to dominate ecosystems in the Devonian, like acanthodians and placoderms and weird sarcopterygians and jawless fishes, have all gone extinct, or mostly gone extinct at the end of the Devonian. And you start to get these ecosystems that are dominated by recognizably modern groups like actinopterygians and elasmobranchs and holocephalans and tetrapods. But the makeup of these ecosystems is very different, like with these holocephalans. Lots of these holocephalans are doing interesting things in these ecosystems in kind of shallow waters that modern holocephalans wouldn't touch with a barge pole. But exactly what they're doing is difficult to work out because almost all of these fossils, these things, are kind of heinously flattened. They're just sort of interesting body shapes splattered onto rocks. But there is some exceptions. So in this talk, we're going to be talking about Inioptera. And Inioptera is an Iniopterygian, which is a group of these very strange-looking Carboniferous fishes you can see in the top left. And these guys are stem group holocephalans. So they branched off the holocephalan branch before the crown group diverged. And almost all the Iniopterygians are flattened. You can kind of tell they've got interesting body shapes from these fossils, but it's very hard to do anything with them functionally. But there is one exception, and that's Inioptera. And Inioptera is known on the basis of these 3D fossils of the skull and the jaws and the pectoral gill and the gills described by Alan Pradell in a series of papers over the last decade and a bit. And this provides an Iniopterygian opportunity to investigate functional morphology in one of these Carboniferous holocephalans, which is what we did in this study. So first off, kind of a comparison between Inioptera and living holocephalans. It's kind of similar to living holocephalans, which is obviously how we know it's a holocephalan. It's got these big eyes. It's got this holostylic neurocranium. It's got this enormous carata hyle, kind of the lower part of the hyoid skeleton. Its gills are packed beneath the brain case. And the first thing we did was to try and reconstruct the muscles in Inioptera with reference to elasmobranchs and holocephalans. And it seems to make sense the most with quite a close reconstruction to holocephalans. Like holocephalans, it seems to have this big this big mandibular adductor, which has a preorbital insertion, which looks kind of weird, but all the bits of the brain case are kind of rearranged in a similar way to living holocephalans. And it's also got this very strong link between the pectoral girdle and the back of the head, which is something else that we see in living holocephalans. But there are some differences. It has tooth walls rather than big tooth plates, although some Iniopterygians have kind of pharyngeal plates. It doesn't have labial cartilages. Its scapular coracoids are kind of oriented front to back instead of side to side. It's got this enormous basibranchial skeleton, which is so super chunky, and it has this weird kind of functional articulation with the pectoral girdle, which is very, very strange. So it's got this strange stuff going on. And it has been suggested on the basis of flattened stuff mainly, that Inioptera and Iniopterygians, so at least some of them were durophages. Inioptera was a durophage. So first we decided to set out to see if that's kind of feasible, which we suspect is a bit fishy on the basis of this comparison. So first we started off with working out how wide Inioptera could open its mouth. And we can do this because we've got this preorbital mandibular adductor muscle that we know the insertion and origin of. And we used the methods of Lautenschlager, which Luke went through in an earlier talk. And so basically muscle has a certain amount it can extend. And we modeled this muscle as a pair of cylinders. And basically using the Lautenschlager's methods, and basically when these are green, they're in the optimal extension range. When they're yellow, they're out of the optimal extension range. And when they're red, they couldn't physiologically contract after extending that far. So this gives us kind of a limit on how wide Inioptera is opening its mouth. And the answer is not very wide. It doesn't seem to be kind of very likely to be rooting around on the seafloor like living holocephalans, which is something you might have guessed from its up to the mouth in the first place. And this also kind of gives us some constraints under which to look at its functional morphology. So how does Inioptera's mouth perform mechanically compared to living holocephalans? Well, again, using these 3D models, we looked at the kind of mechanical advantage in 3D over the course of the opening cycle, and we used the inferred surface area of the muscle attachment to estimate how much force it was producing. And again, the answer is not very much. The mechanical advantage of Inioptera is very low. Inioptera is the triangle. It's plotted against a data set of living chondrichthyans from Motter and Huber. And extant duraphages, which are the circles, the blue circles around, have a very, very high mechanical advantage, whereas Inioptera doesn't. It's pretty weedy. It's kind of down in the bottom left of things. And the force, which is a bit more of an estimate, is also pretty weedy. Inioptera comes out kind of in the bottom of living chondrichthyans, and the duraphages are far higher, as are kind of sharks that are crunching things up. So it doesn't seem very likely that Inioptera was a duraphage on the basis of those various things we've just gone through. So if it's not a duraphage, what is it doing? Well, if we go back to our comparison with a living holocephalan, one of the key differences is it's got this absolutely massive basibranchial skeleton, a massive basibranchial element, and this kind of weird functional link. And if you found this in a tetrapod, this would suggest that it was an aquatic tetrapod. This would suggest that it was doing suction feeding. And so we kind of decided to have a think about whether Inioptera more broadly kind of fits with that. So the first thing is whether it has this anterior mouth aperture. So usually Inioptera and Iniopterigians are reconstructed in paleart with these big yawning gapes, which are sometimes slightly terrifying. But based on our reconstruction of the mandibular adductor, this would have actually have occluded the sides of this gape. So it seems more likely that Inioptera's mouth is kind of limited to an anterior opening, and these kind of reconstructions probably aren't quite right. And this is actually kind of backed up if you look at where the teeth are in flattened specimens of Iniopterigians. They're concentrated right at the front of the mouth, which is also incidentally the bit below mechanical advantage, and they're all oriented anterior in these kind of anterior rows, which also suggests that that food is coming into the mouth from the front rather than from the sides. As if you imagine a shark, it has all of its teeth are kind of pointing over the sides of its mandibular rami. So this kind of matches what we would expect to see in something that's suction feeding. It has this anterior mouth aperture. The second thing is an expandable pharynx. So as we saw, Inioptera has this very strong link between the back of the neurocranium and the top of the shoulder girdle, like holocephalans, but in Inioptera it seems even more so. It's got these enormous fossae in the back of the head and these big surfaces on the scapular coracoid, which are oriented anteriorly towards these fossae. So we infer this as meaning there's a very strong muscular attachment at the top. There's also big surfaces on the bottom of the back of the scapular coracoid for hypaxial muscles to insert, which suggests that it's pulling back on the bottom of the scapular coracoid. It's also got this very chunky basibranchial skeleton, which suggests it's got large attachment areas for coracohyoid muscles that are important in contracting kind of the bottom of the pharynx if you're trying to expand your pharynx. So this seems to match again with what we would expect to see in a high-performance suction feeder. But does its pharynx actually expand if you mess around with the model? Well, we built a little animation of Inioptera, and we use this blue kind of shape is measuring volume, and it's kind of outputting volume via Python code. And when you pull back on the bottom of the pectoral girdle, the pharynx does indeed seem to expand fairly impressively, kind of between 150 and 160% on this. And so this seems to match again what we would expect from a suction feeder. This is only moving backwards and forwards. It's got these massive keratohyals, which are out of sequence with the gills, unlike in living holocephalans, which would presumably also provide lateral expansion. So basically, we think on the basis of these two things that Inioptera meets the requirements to be a high-performance suction feeder. This is interesting because it suggests that at least some of these holocephalans are filling these kind of free-swimming suction feeding niches now filled by Neopterigians in these Carboniferous seas. And in a sense, it's kind of solved this problem with this very holocephalan-like morphology in a way that's kind of more comparable to tetrapods than to other fishes that you get around today. And this also kind of begs the question of whether holocephalan anatomy, which is very closely associated with duraphagy, maybe it's actually got some of these anatomical characteristics that are now duraphagous, might not actually be as closely associated with duraphagy as we think. So thank you for listening, and thanks to all these people for helping with the research and paying for me to do the research and paying for me to come to virtual Manchester. And that's it.
Thank you, Richard. That was great. Definitely, I've been keeping an eye on the Slack channel, and so far, your favorite comment and what everybody seems to have taken out is the walrus can suck the skin off a dead eel. So, but you had everyone's attention. Thank you so much, Richard. So our next and last talk for the session is by Hugo Dutel with how in vivo data can shed light on jaw evolution during the fish tetrapod transition. So Hugo, if you want to go ahead and get started.
Yeah, I can share my joke. Okay. Oh, merde. Désolé. Sorry. So does it work?
Yep, we can see you just fine.
Okay. Everything works? Okay. So, hello everyone, and thank you for giving me the opportunity to talk today. So the emergence of tetrapods entailed dramatic changes in the vertebrate body plan, and especially in the head. And now we better understand the sequence of the change, but how they relate to the evolution of the feeding function is still unclear. And because of the dramatic difference in the physical property of water and air, the shift from aquatic to terrestrial lifestyle is expected to be reflected in the functional evolution of the head, with a trend toward a higher bite force and slower movement of the jaw in terrestrial vertebrate, basically a static pressure system. But there were studies on fossils that collected evidence that are conflicting. So suture morphology in Acanthostega suggests that it was primarily using biting to capture its prey. So the static pressure system will have emerged before the invasion of land. But the analysis of jaw shape and their structural mechanics have demonstrated similarity between early tetrapods, sarcopterygian fish, and terrestrial tetrapod. And jaw shape and its mechanical parameters that are measured on fossils appear to remain surprisingly stable until the Permian. And the analysis of jaw of fossils suggests that the morphological and functional change allowing organisms to generate higher bite force appeared after the invasion of land. So there's been study on fossil, as I've shown you, but we do not have data, in fact, so much data on the form-function relationships in living taxa spanning the fish-tetrapod transition. And using living and fossil taxa, we here aims to understand how changes in the head form relate to the evolution of the feeding function. So first, we are characterizing the pattern of variation in jaw shape across living bony fish, and we want also to compare this taxa with fossils. So we have sampled the jaw shape for 52 species that span the fish tetrapod transition, and to perform a geometric morphometric analysis. And we got a principal component analysis with the two first axes that describe 60% of the variance. The first axis describes the change variation in the depth on the mandible and the proportion of the region behind the tooth row, while the second axis describes the curvature of the mandible and the changes in the notably proportion of the region behind the jaw joint. We can see that there is a large overlap between in the morphospace occupied by sarcopterygian and actinopterygian, but they also show distinct regions. So if we look in more detail within sarcopterygian, we can see that there are different distinct groups that occupy distinct regions. So there is a certain proportion of phylogenetic signal in our data. So we can see amphibians, Sicilian salamanders, and amniote with a mammal being quite separated from the other tetrapod. This is reflected in the shape of this extreme here on this axis. And living sarcopterygian and fossil sarcopterygian fish are around the center of the morphospace, close to salamander and certain lizards. So with the lungfish and the robust jaw being very distinct from coelacanths, and the Eusthenopteron being separated from Latimeria along PC2. And stem tetrapod with Acanthostega here are separated along PC1 from sarcopterygian fish, lizard, and reptile, because they have a quite, in fact, a gracile jaw. So we also find here that there is, in fact, between the jaw of sarcopterygian fish, stem tetrapod, and non-mammalian living tetrapod. So now, to understand the factor underlying this pattern of variation, we need to better understand the form-function relationship in living taxa. So with Anne-Claire Fabre, we have been measuring in vivo bite force and feeding kinematic on living animals. We used phylogenetic regression to test the relationship between jaw shape, bite force, and ecology on a subsample of 32 species for which we have in vivo bite force. In fact, data collection has been quite affected by COVID. And bite force is a significant predictor for jaw shape, but not ecology. And higher bite force are associated with deeper and shorter mandible. Taxa that are phylogenetic distant can be functionally close. In fact, that's interesting. But also, we can notice that the same jaw shape can be associated with very different biting performance. So this is a preliminary result. We have a lot of analysis and data also to sample, but it's just to give you a flavor of one of the aspects of we are investigating with in vivo data. We are also interested in understanding how muscle anatomy, which is not preserved in fossil, relate to skull form. So based on this section, we obtain muscle mass, fiber length, physiological cross-section area in different animals, and we also compile data from the literature that's were obtained following the same protocol. And this result shows that PCAC, physiological cross-section area, scales with lower jaw length, but there are not obvious difference between the different species sampled. And also, there are no obvious difference between the lifestyle of the different animals. Sorry, the cat is quite annoying. So we have started to explore the relationship between jaw shape, musculature, and functional performance. But our goal also is to understand the underlying machinery between function and skull shape. And for this, we are employing biomechanical modeling. So by the dissection and 3D reconstruction of the anatomy, we are simulating the functioning of the musculoskeletal system as the animal generates a static bite on the prey and during mouth closure from maximal gait. And this allows us to derive parameters that are hard or impossible to measure, like joint reaction force, in order to explore how the musculoskeletal system, the way it functions, relate to head form, and also the potential trade-off between force and speed generation. And it is very important here to calibrate and validate this model against the in vivo data for different species, in fact. And I will focus only today on the validation process of these models. In fact, obtaining in vivo data is here critical. As you can see here, in this sensitivity analysis, in this laser, the way that muscles are reconstructed impacts the bite force predicted. When muscles are not reconstructed in a model in a very accurate way, there can be up to 34% difference between the simulated and in vivo bite force. So we compare the model, the model we are doing measure on different species. Here, scale to in vivo bite force, scale to head width for comparison. So, for instance, we can see that the axolotl has a lower bite force than Polyperus and the tiger salamander. And compared to in vivo measurement, a model tends to underestimate bite force, but what is still okay is that the output shows the same trend as the in vivo data. So the dynamic model, now it's a bit more complex. It includes also external forces that counteract the action of muscle, such as the drag, the inertia, and the resistance of the tissue. And this is a more challenging model because also the force generated by the muscle is a function of the shortening speed, the change in fiber length, and change in the pennation angle. So it's really important here to have in vivo data to assess these models. So we compare the in vivo kinematic profile measured with high-speed video record with the model output. Here is the gap from open to almost closed gap for different time steps, for two species, Polypterus and the axolot. And you can see there is a good match between our model in blue and the experimental data. The model also predicts well the maximum magnitude of the jaw closing velocity, so the time derivative of this first plot. But you can see that for Polypterus, we got then a good estimation of the acceleration, but there is a big mismatch for the axolot. In fact, a small error in the velocity leads to a very big difference in the estimation of the acceleration because of the derivation. But still, our model is quite good at estimating the maximum jaw closing velocity, which is a relevant metric.
30 seconds, please.
Oh, yeah. So this model, so basically it's what we can see with this model that in vivo data are important to calibrate and determine their accuracy, but also it allows us to safely know what are the variables that can be accurately predicted. Especially because after we want to use this model across a broad range of species for which we won't be able to collect all the experimental data. So to conclude, the output of a model show a good match with the in vivo data, and the in vivo data are really important to decipher the functioning of the musculoskeletal system. And as I was saying, we are sampling more living taxa, but also try to use the shape analysis and relationship between hard and soft tissue we can derive from living taxa to try to reconstruct the musculature in fossil taxa and then do biomechanical simulations. So thank you for your attention.
Thank you, Hugo. And thank you again to all of the amazing speakers in the session, Comparative Morphology and Feeding. And you guys have been having some wonderful comments and questions. So
sorry for the cat.
Don't worry. I think everyone has a cat, dog, or child who has been demanding their attention. Probably even somebody with the boa constrictor hanging around as well. So if I could go ahead and get everybody, all the speakers on and unmute and show your video, or at least show your video in the very least. So yeah, we've been getting some great questions, and you guys have been doing a great job replying from what I can tell, as much as I can multitask of listening to you, to all of these great talks, as well as monitoring the Slack channels. Obviously, as I commented before, there have been lots of questions about how does this suction feeding work, especially obviously with the with how does a walrus suck the skin off a seal, but also with other ways that you can learn more about Inoptera. So is there anything that you'd like to expand on that you've gotten with your questions?
Yeah, I'm not sure I'm professionally competent to talk about the walrus sucking the skin off a dead seal, but I could answer Ben's and Lisa's question, if that would be useful. So for Ben, I mean, I've kind of already typed a comment, but I think that basically I'm not very confident that the muscles that open the mouth are very well constrainable in terms of exactly where they are. There's quite a clear adductor fossa for the mandibular adductor, which is closing the mouth, but for the ones that are opening the mouth, which is the coraca mandibularis in living holocathens, I think it would be difficult to estimate how big it was. But it might be cool to try. I just don't know if you'd arrive at a very good answer. And I think the same kind of applies to the suction, because we don't really know how much the pharynx is expanding laterally. But maybe you could use our kind of anterior posterior model to arrive at an underestimate, and then use that to kind of argue your case. And for Lisa, who's asked about sibirhynchids and Idiopteryginae, which, so I kind of didn't talk about this, but Idioptera is a member of the sibirhynchids, which means Idiopterygians which have their upper jaws fused to the brain case. But there's another group of Idiopterygians, which is only known from flattened remains, which have separate palatal quadrates like other fishes. And this is something that holocyclians seem to do in the Carboniferous, is some groups have fused palatal quadrates and others don't. And so for the ones that do have fused ones, again, all the fossils are flattened. So maybe they were doing the same thing as in the opera. They seem to have kind of the same kind of pharynx bones and things knocking around in the flattened fossils, and they have these anteriorly pointing teeth. So possibly the ones with the separate palatal quadrates, I think it's kind of difficult to work out what the adductor mandibularis is doing. But maybe it's attaching in the same place. It's not impossible. These kind of palatal quadrates do have kind of go quite far anteriorly. But it's kind of difficult to answer this question without pictures. But so I don't really know is the answer to that question. And that was my answer.
Thank you. It is always challenging. You always want to have those kind of backup pictures at the end of your presentation ready to go. But great. No, thank you so much. Now, Antonio, you've been getting some really interesting questions with your work. Is there anything that you would like to, and you've been answering them in the chat, is there anything that you would like to expand on with these questions?
I have I had a question from Emilia, and so yeah, the thing is that about lateral loading of the tooth models, and so the what I was saying is that basically early dinosaurs, we didn't think they were using complex jaw movements from their skull morphology, except for some early ornithischians, for example. So we basically loaded the models with a simple vertical force just to keep it consistent and make things comparable. It's very interesting. It's a very interesting questions, because some ornithischians may have had some sort of complex jaw movement in lateral or anterior posterior direction.
Oh, thank you so much. It was really interesting. So what do you think is the most surprising result when looking at the teeth of early dinosaurs that you've found so far?
Well, our results mostly agree with previous interpretations of the just looking at tooth morphology. But it's usually the sauropodomorphs that are more difficult to interpret, because there's a wide spectrum from the earliest ones which have curved and blade-like teeth to the ones that have denticulated spear-shaped dentitions. So the importance of the study is that we are now in those intermediate taxa. We are now quantifying all those shape and functional differences with these methods.
Oh, fantastic. No, thank you so much. And Case, let me try. You've got, and I completely agree with Sean on this. It was a really well-written talk, and you had a lot of information going on, which is fantastic. And so his question is, what kind of shakeups have you seen from the more recent works?
And so he clarified in the thread that he's specifically saying, like when I mentioned that because the results are preliminary, there were some things that have changed. So all these are from our wonderful reviewers that realized there were some errors in our data analysis procedures. And so the biggest thing is that there's actually some, even though there's not a whole lot of variation in diet, in the paleoecological categories there is. There's like some clear ground group, a ground/raptorial, and arboreal/raptorial. So it's possible they're eating similar things in different areas. And of course, though, Shinjing-ornis, again, is indeterminate in that. So still have no idea what's going on there.
Yeah, I did actually want to follow up and ask a question. With these different birds, are they all found in the same environments, or are they found in a variety of environments at this point?
All from the same group. The two formations within the group, relatively few horizons. So these are more or less contemporaneous. Langipteryx spans the whole time. The other ones are only known from one or two individuals.
Okay, and so is it kind of a near shore environment, or are we dealing with more of
lacustrine?
Lacustrine. Okay. All right. Fantastic.
With noted volcanism, a lot of the mass die-offs that preserve it so well seem to be driven by volcanic cycles.
Okay, great. No, thank you. And then let's see, I do have, let's see, just looking through. And with Hugo, so looking at the, so far, with your future models, so you had talked about using, doing the wrapping with the modeling with your musculature versus the results from the musculature just being a straight attachment. Are you going to be looking at that further with the wrapping of the musculature with your, with the future work that you're going to be doing?
Yes, I mean, it's just muscle wrapping basically is just, a term to say the muscle are reconstructed correctly. It's, I think, just to illustrate, especially in a paleontological conference, how musculature is really, a muscle architecture is really important and really affects the results. So it is data I generated for another project on lizard feeding mechanics, but it really illustrates well how, and graphically as well, how the orientation of the different muscle and muscle bundles can impact the result. And I think it's really something to keep in mind. And that's why in vivo data, even for more simple, let's say, anatomy, I think it's really important to have in vivo data to have an idea of where we are.
Absolutely. It was very interesting to see the difference between the in vivo and the modeling data and where that sat with each other. And especially that the bite force wasn't nearly as strong or compared to the in vivo results with the modeling. And so that was very interesting.
Thank you.
You're welcome. And I just got one more quick question. And this one is for Richard that just came through. And I'll try not to let my Americanism show too much by saying holocephalon. Oh, no, sorry. Still did that anyway. Holocephalians. So assuming Iniopterus was a suction feeder, does the pectoral fin structure suggest a slower swimming animal, characteristics found in most suction and filter feeders?
So, yeah, regarding holoceph and holocephalon, I don't know if either is right, so I forgive you. I did get asked that in a job interview recently, which was pretty weird, which was correct. Anyway, so the pectoral fins, people have kind of looked at their pectoral fins, but not kind of that closely functionally, I don't think. I think I remember seeing an abstract. I didn't go to SVP, but I think I saw an abstract there, so maybe someone is working on this, which would be pretty cool. So I don't really know the answer to that. They have been compared to kind of eagle rays and stuff with these really big kind of dorsally located fins. And regarding the second bit, yeah, there are some other weird ones. The famous ones are the ones with the big tooth walls, like Helicoprion and stuff like that, which are supposedly eating kind of soft-bodied prey by whacking them with them. There's ones that are kind of starting to be duraphagous, but with lots of different body shapes, like Chondrincellus, which is a really long eely one with tooth plates. And lots of them just look kind of like sharks, like Mike Coates and colleagues had a paper earlier this year about how one was kind of a generalist feeder and had an unusual jaw mechanic where it opened the jaw and then ate things with its kind of shark-like jaws. So they're doing loads of different things, I think.
Cool, thank you so much. And so I want to thank everyone again, all the speakers for their great talks. And I want to thank the audience for attending, and keep the questions rolling in the Slack chat, and our speakers will gladly just kind of monitor it and help to answer questions as we go.
Thanks, Victoria. Just before we disappear quickly, just a couple of housekeeping announcements. I also echo Victoria's thanks for all the speakers. There were some really great talks there, and also Victoria's thanks for marshalling everyone. Thanks to Victoria for marshalling everyone so effectively. We will be starting again at 1:30 for the Paleozoic and macroevolution in the non-parallel sessions. And there's also people are interested in ethnic minorities and allies Zoom session starting just now. Links for that can be found, details for that can be found in some of the Slack channels. So I'll pass you back to Victoria and say see you later this afternoon.
Thank you, Rob. And again, thank you, everyone. And stay tuned for some more amazing talks coming up this afternoon and some great sessions, as Rob said. So check your Slack channels to check out all the great things going on.